away over here, long flight, and so in the middle of his teaching semester, so he very much appreciates that he's made it. And so I guess I don't really have to introduce Mark to many of you, but I'll just give some very brief overview. So he did his doctorate degree at the University of California, Berkeley, in 2005, and then went to Princeton University for a Hubble Spitzer postdoctoral fellow, and then went to the University of Santa Cruz in 2008 as assistant professor, and then in 2012 he's associate full professor at the University of Santa Cruz. And so he is an expert on star formation and simulations of star formation, and today we will speak about the origin of stellar masses. And so looking forward to hear your talk, and welcome to Heidelberg.
Thank you. So I have to say, I was prepared for many things related to this talk, but giving it while wearing a cowbell was not one of them. So I am going to hopefully leave you today a little bit better informed about why stars have the masses they do. That's the fundamental topic I want to tackle in this talk. Where does n-sun come from? Why is the typical star the mass of the sun, or a little smaller than that, and not, say, 1,000 times higher in mass or 1,000 times lower in mass? So that's the big idea that is going to animate this entire talk. All right, so here's the overview. I'll start with an I will be quiet for a moment. Okay, let's see. Is that?
Yeah.
Okay, good. Don't need to deafen the audience any more than I'm going to. Here's the overview. All right, so I'll start with sort of an introduction for those who do not think about this class of problems, and then I'll discuss some observational constraints on stellar masses. I'll spend the bulk of the talk, since I am, of course, a theorist, on models to try and explain where the masses of stars come from, and then I'll summarize. All right, so let me start with, for those of you who don't do this at all, what is the IMF? All right, when we talk about the initial mass function, what is that? All right, quite simply, it's the mass distribution of stars at birth, and by at birth I mean for a population that formed Thursday and that has not had any stellar evolution happen yet. All right, so it's the mass distribution of stars before any of them have blown up, before any of them have lost any mass by stellar winds or anything else like that. All right, so that's what we mean by the IMF. Now, I know some of you in the audience are cosmologists, and you're naturally thinking, why should I not go to sleep right now? All right, so it's always a good question to ask when you're sitting in a float. Here's why you might care about the IMF even if you are, in fact, a cosmologist. All right, it's the stellar mass distribution. First of all, it is one of the most fundamental problems in astrophysics. It's one of the longest-standing unsolved problems in astrophysics. All right, you think it's a really basic question. Why is the typical mass of a star what we observe it to be? That question's been around for at least a century, and we still don't have a fully satisfactory answer. All right, it underlies most extragalactic observations in theory, and what I mean is that in the vast majority of cases when you're looking at an external galaxy, what you get to measure is the integrated light of the stellar population. You don't get to see the individual stars. And in order to infer anything about the properties of that stellar population, you need to have some model for the underlying mass distribution of the stars, the IMF. Similarly, if you're doing theory and you want to think about, for example, how galaxies form, well, the stars, the contribution of stars to stellar feedback to the energetics of the ISM is all determined by the IMF, and that's the next point. All right, the IMF determines the energy and chemical balance of the universe, and the reason is that there are two significant sources of radiant energy in the universe: black holes and massive stars. Massive stars are much more efficient nuclear engines than low-mass stars. They turn hydrogen into light and heavy elements much faster than low-mass stars. And so, when I form stars, the balance of high-mass stars versus low-mass stars is critical in determining the amount of energy I'm going to get out of the stuff I put into stars and the amount of heavy elements I get out. So you need to understand the IMF if you want to know anything about the efficiency with which galaxies turn their gas into radiant energy that we can observe and heavy elements that we can measure and that we are made of. And finally, the IMF determines the suitability of the universe for life. If the typical star had the mass of Saturn, there would be no warm planets heated by stars fusing hydrogen into helium. Right? There's no reason the ISM couldn't make as its typical object something that was supported by degeneracy pressure and never ignited hydrogen. How does the ISM know anything about nuclear physics? How does it know to make stars that are warm enough that they can fuse hydrogen and they can give rise to planets where life can evolve? Now, of course, you could appeal to the anthropic argument, but that would be a cheap and really lazy way out. So let's see if we can do a little bit better. All right, so I mentioned this is one of the oldest, longest-standing problems in theoretical astrophysics. And just to prove that to you, I have a little historical aside here. The question of the IMF is addressed in a number of places, but one of the earliest and clearest statements is in this Beccarian lecture that Arthur Eddington gave in 1926. All right, and this is actually, it's worth reading. You can find this on AstroPH or on Archive, on ADX. It's remarkably prescient. All right, so remember, this is 1926. No one has ever observed the ISM in anything other than nebulae being lit up by bright sources, right? No one had ever received a radio photon. All right, and Eddington successfully deduced from sort of pure thought the characteristic temperature of the ISM, the characteristic ionization state of the ISM, and the characteristic density of the ISM. And he managed to get all of those right from more or less pure thought. He's a pretty smart guy. But one of the things he talked about in this lecture is how the ISM might form stars and what gives rise to the characteristic masses of stars. Now the amusing thing is, so this lecture was given, it provoked a response. So here's a response, and this was actually published in the Observatory by James Jeans. And it's worth reading. Let's see. This is how he concludes. So much work has been done on isothermal equilibrium that it is difficult to understand how Professor Eddington can harbor the illusion that he is doing pioneer work in unexplored territory. Yet his complete absence of reference to other theoretical workers suggests that such is actually true. So in other words, this is a letter from Jeans complaining, you didn't cite me. All right, so if you think that like nasty emails complaining about not being cited are a modern development, they are not. All right, they go back to at least the 1920s, and it could be worse. You know, if you get one of those emails, just think. It could have been sent by James Jeans and published for everyone to see. All right, so this is Jeans's response. And what he's really complaining about is that Eddington did not cite the paper on what we now call the Jeans instability. Eddington responds. It goes back and forth like this for a while, and you can find all of this on UDS. Let's see, he says, Dr. Jeans deals rather severely with a portion of my Beccarian lecture. And this is what he says about the Jeans instability, and there's actually some deep insight here we'll get to in a moment. He says, I had long admired this ingenious paper, referring to the paper describing the Jeans instability, but having come to the conclusion that the masses of stars are determined by radiation pressure independently of the primitive density, I ceased to accept it. All right, now he's actually making a subtle but important point here. All right, now, Eddington knows that stars have very special masses. Now, the reason why he thinks they're special isn't what we understand today. Jeans doesn't know about nuclear fusion. Right, but he does know that stars have masses where radiation pressure is just starting to become important. If you read his book on stars, all right, he says, gives the following thought experiment. Take spheres of gas and just calculate their hydrostatic equilibrium. All right, and do this for a sphere of gas that's 10 to the 1 grams, 10 to the 2, 10 to the 3, and there's a number of them, etc. And he says, and you will find that the first 32 or so are completely boring up to 10 to the 32, totally dominated by gas pressure. All right, numbers 35 and above, also completely boring, totally dominated by radiation pressure. The masses of stars, however, are right in that interesting regime where you're starting to switch over. All right, and he says that can't be an accident, right? How does the Jeans instability tell me anything about that? right? That doesn't tell me, there's nothing in the gene's instability that obviously picks up that mass. So that's why Eddington is saying he doesn't believe Jeans's paper is relevant to the masses of stars. And it's a subtle and important point. Now, today we would say that the masses are special because of nuclear physics, because stars have masses right where nuclear fusion starts up. And this is, of course, not unrelated to the importance of radiation pressure. That is still a challenge to understand in the theory of star formation. We'll come back to that. But it actually goes on. Here's Jeans's response to Eddington's response. May I conclude by assuring Professor Eddington it would give me great pleasure if he could remove a long-standing source of friction between us by abstaining in future from making wild attacks upon my work which you cannot substantiate, and by making the usual acknowledgments whenever he finds that my previous work is of use to him. So this is great. I mean, you can imagine these two, sort of distinguished Edwardian gentlemen in their, coats and cravats, and it's this very, very mannered language. If the learned gentleman would only remove his head from his own hindquarters, he would see that, etc. It actually goes on past this, but I'm going to move on. There's a whole series of letters, well worth reading. All right, so before I jump into the theory, let's start with what do observations tell us about characteristic masses of stars? What do we see? All right, there are really two ways of going with this problem. One is you can work on resolved star populations. That is, regions that are close enough that you can actually just go and count the stars one by one. All right, you can do this in the galactic field. And if you do it in the galactic field, the advantage is there are a whole lot of stars, and you get great statistics. All right, the big disadvantage is that you can't really do anything above one or a few solar masses because of stellar evolution. Right? The vast majority of the stars in the galactic field are order of 5 gigayears old, and everything that's more massive than a few solar masses has long ago died. All right, so you get great statistics sort of near the peak of the IMF at low masses, but very poor constraints everywhere else. The other thing you can do is go look at young clusters. All right, if you go look at sufficiently young clusters where there's been no stellar evolution, then you can say something about the IMF going up to very, very high masses. The great disadvantage is, of course, the statistics are worse, and you have to rely on pre-main sequence evolutionary tracks in order to infer the masses of stars, because a 1 million-year-old one solar mass star hasn't actually reached the main sequence yet. All right, so those are the sort of two techniques we have. And for the young cluster technique, the best case is probably this one. This is the Orion Nebula cluster, a few times 10 to the 4 stars, order of parsec in size. Right, each of those dots there is a star that has been placed on a pre-made sequence track as an individual correction for its extinction, and you can go and try and figure out what the IMF is. All right, and when you do that, you get something like this. All right, so this is from Nicola de Rio's work. All right, so x-axis is log of mass and solar masses, y-axis is just frequency of stars in that logarithmic mass bin. All right, what you see is that this is sort of reasonably well fit by something like a log normal distribution. All right, and in particular, there's a distinct peak at sort of like 0.3 solar masses. All right, so that's what you see in this particular region. You can repeat this exercise. The data is not pretty in other regions, and here's what you get. So here are from two recent reviews in 2010 and in 2014. All right, and what you see is that near the peak, you do characteristically get some sort of log normal, which is centered between 0.1 and 1 solar masses. And I don't want to make too much of, is it at 0.2 versus at 0.5? I don't think the systematics are under control well enough that you can really tell the difference. What I want you to notice about all of these distributions is that they are generally consistent with there being a characteristic peak somewhere between 0.1 and 1 solar masses. And these are wildly different regions, I should mention. All right, so here we've got, for example, Taurus, IC348, Sigma Orionis, and the ONC. If we just compare the ONC to, say, Taurus, we're talking about a difference of about 3 orders of magnitude in stellar density. All right, so this peak seems to be in roughly the same place, even when I change the density of stars and the absolute number of stars by many orders of magnitude. All right, now, above that sort of peak, at higher masses, you see this sort of power law tail. All right, and that power law tail has a slope of either about minus 1.3 or minus 2.3, depending on whether you like dn, dm, or dn, d log m, and that's the famous saltpeter slope. All right, and again, you get that sort of to first order everywhere. So I don't want to claim that there's no variation, but I will claim that given that we have many orders of magnitude variation in the number of stars and the density of stars, there is surprisingly little variation, and perhaps none at all. So that's a challenge to explain our theory. All right, now, the other thing you can do to observe the IMF is you can go after unresolved star populations. All right, and the challenge there, of course, is that you can't count the individual stars. You need to have some way of inferring what the underlying IMF is, but you don't get to see every single star. All right, and one way of doing that is you can use integrated light. All right, so that is, you can say, if I had a certain IMF, I expect that the summed light output I can see would look like this. And you can do that either through colors or from the spectrum. All right, or you can do it from kinematics. You can try and constrain the mass to light ratio kinematically, and then you can compare it to what you would expect for a given IMF. All right, and the great advantage of this is that you can actually do it beyond just the Milky Way and Magellanic Clouds, whereas with resolved stellar populations, you're basically limited to just those systems because further away you just can't resolve the individual stars. All right, and so far there have been two regimes that have been explored fairly well using integrated light. One is dwarf galaxies, and the other is giant ellipticals. More distant spiral galaxies are coming, but they're going to take a little longer. All right, let's talk about the dwarfs first. So those of you who have been in this field might remember there's some excitement a few years ago with a claim that dwarf galaxies had a different IMF than the Milky Way. And the basis for this claim was H-alpha emission. All right, so let me explain how this argument works. H-alpha is produced when ionized hydrogen moves your bonds. The rate of H-alpha production is proportional to the rate of ionizing photon injection. And ionizing photons are produced predominantly by the most massive hot stars. So if you take a sort of canonical type IMF and ask, what's the 50% point for ionizing photon production? That is, stars of what mass produce half the ionizing photons? The answer is 50 or 60 solar masses. So things above 50 or 60 solar masses make half the ionizing photons. All right, so H-alpha is really telling you about the very upper end of the mass distribution. Now in contrast, you can compare that to FUV light. And FUV light is telling you about stars that are more like 10 solar masses. All right, so in principle, the ratio of H-alpha to FUV emission is telling you something about the ratio of 50 solar mass to 10 solar mass stars, and thus constraining the upper end of the IMF. And the excitement was this data. So if you look at this figure, x-axis is FUV luminosity, y-axis is H-alpha to FUV ratio. And in principle, this ratio should only depend on the IMF. And what you see is that if you go to higher FUV luminosities over here, you do get back to something that's sort of flat, but as you go to lower FUV luminosities, you get this sort of turn down. All right, so does that mean that dwarf galaxies, those are predominantly the things over here on the left, are deficient in massive stars relative to low mass stars? Well, yes and no. Yes, it does, but that doesn't directly tell you about the IMF, and here's why. All right, the problem is, these galaxies have really, really low star formation rates. And H-alpha producing stars have very, very short lifetimes. So imagine a dwarf galaxy that's just trickling along, forming stars at 1/100th of the solar mass worth of stars a year. About 1/100th of the Milky Way's rate. So you get a little trickle of stars forming, then nothing, then a few more. Now imagine you go and observe this dwarf galaxy, say, 5 million years after the last little burst of star formation happened. Well, the stars that produce the FUV light are still around because they have lifetimes bigger than 5 million years. But the stars that produce the H-alpha, they're all dead. They all die in 3.5, 4 million years. And so your H-alpha to FUV ratio will be depressed. And that's really telling you something about the mass function. It's telling you that you have a deficiency in 50 solar mass stars compared to 10 solar mass stars. But it's not telling you about the initial mass function. It's telling you about the present day mass function. So if you want to know about the initial mass function, you need to then make a model and take this effect into account, and that's what's shown here. All right, or actually up here. So this is a model that takes into account that stochastic flickering. The green here is just the distribution of H-alpha to FUV ratios from a model with a completely normal IMF, but taking into account the stochastic flickering. And you'll see that it also exhibits this turn down. All right, and that's, again, just reflecting the fact that at a very low star formation rate, you've got a good chance of catching the galaxy at a moment when it's got fewer massive stars compared to its UV light. All right, and then you can ask, well, is the data consistent with what you observed? And that's what's shown in the x-axis. All right, so the x-axis, or on this bottom plot, the x-axis is FUV luminosity. The y-axis is H-alpha luminosity of the model minus H-alpha observed luminosity, divided by the expected dispersion at that FUV luminosity. That is, if I take the distribution of H-alpha to FUV ratios and I normalize by the dispersion I expect just from the stochastic flickering, and you see that the data are perfectly consistent with a Gaussian with a mean of 0 and a standard deviation of 1. In other words, they're totally consistent with the normal AMF plus stochastic flickering. All right, so I put this in here in part as a cautionary tale. When you're working with integrated light, be very, very careful you understand the systematics, or you can make a big mistake. All right, so this claim IMF variation we can get rid of. It's wrong. There's one more that's maybe a little more convincing. All right, and that has to do with in giant elliptical galaxies. All right, there are two independent lines of evidence, and I've only put one of them up here for simplicity, which is the kinematics, and that is from dynamical modeling of a giant elliptical, you can try and infer the mass to light ratio, and you can moreover try and separate the dark component of the luminous component. And what you find is that for galaxies that have fairly low velocity dispersions, that's things indicated in blue here, these are early galaxies, you get a mass to light ratio that's sort of consistent with a normalish IMF labeled Krupa or Chabot here. But as you go to higher velocity dispersion halos, you seem to need a higher mass to light ratio, which would imply more low mass stars compared to a normal IMF. All right, now that's one line of evidence, and if that's all there was, I don't think anyone would take it that seriously. But there's a second independent line of evidence in favor of an overabundance of low mass stars, and that comes from the presence of certain spectral features that are unexpectedly strong. And I'm not going to go into the details of that, but there are these two independent lines of evidence. So it seems at least plausible that the IMF is slightly different in elliptical galaxies, in giant ellipticals. Now let me emphasize slightly, we're talking about a change of a factor of maybe 2 in the mass to light ratio. All right, so this is a pretty subtle effect, but it's the best evidence we have so far for a varying IMF. Now, I'm not certain this is right. I think it's probably right, but the history of this field is littered with enough examples of oops moments that you have to be a little skeptical. All right, and I'll say, in progress, trying to do this for spiral galaxies. This is a survey being led by Daniele Calzetti called LEGACY. The Legacy Extragalactic UV survey is a survey of 15 nearby galaxies ranging from dwarfs to spirals, using a bunch of filters on HST going out into the UV, and this potentially gives you some constraints on the IMF too. I won't spend any more time on this, but that's sort of underway. All right, so here's the summary of the observational state. All right, the IMF appears to be a sort of power law of high masses, but with a distinct turnover or plateau at lower masses. All right, and in resolved stellar populations, both the slope and the turnover are consistent with being universal. The turnover is always between 0.1 and 1 solar masses. There's no evidence for variations in the IMF in dwarfs, but there is some tentative evidence that that turnover mass moves to lower masses in giant ellipticals. All right, so that's the state of the observations. So now, let's see if we can make sense of it. And we come up with some theoretical models that will let us understand this. And I'm going to focus on these two parts, the mean mass and then this high mass. All right, so let's start with the high mass. Let's start with the tail of the IMF. We'll do the tail first and then come back and do the dog. All right, so a plausible explanation for the tail. Well, all right, the tails are power. Power laws are great because they're scale-free. Everyone knows the power law. All right, so when you see something like that that's scale-free, you naturally go and say, well, what do I know in the ISM that's scale-free? And a naturally plausible explanation, something that's scale-free, is turbulence. We know that the ISM is extremely turbulent. We know that it is dominated by these supersonic motions that are highly turbulent. Maybe that explains the IMF. So can we make a story out of that? All right, you can try to. So here's my whirlwind tour of the statistics of turbulence, all right? Are there any applied mathematicians who actually study turbulence in the audience? God, I hope not. All right, I'm going to summarize all of turbulence in 2 slides. So turbulence can be described in many ways with many statistical techniques, but one is with the power spectrum. The power spectrum is telling you about how much power there is at different size scales. All right, and it's normally a power law, P to K, this is K to the power beta. For subsonic turbulence, you probably know the famous Kolmogorov scale limit, beta is -5/3. For supersonic turbulence, it turns out you get data goes to about -2. All right, and here's just a demonstration of this from the simulation. What you're looking at here is a plot of K squared times the power spectrum versus K, and you see that it's close to flat. So you get something like a K minus 2 power spectrum. All right, it's dying off here because of numerical effects that you're running out of resolution, and so you get effectively numerical viscous scaling. That's what's happening here at high K. All right, so statistics of turbulence. We also know that turbulence generates, supersonic turbulence, a roughly log normal distribution of densities. All right, so let me unpack that statement. What I mean by that is that if you take a turbulent medium, where it's got supersonic turbulence, you measure the density at a random point, you get some value. Measure the density at another point, you get some value. Do this many times and just plot the probability of measuring some density versus density. What you will find is that you get something that is a Gaussian distribution in the logarithm of density. All right, now this is at some level not surprising. This is a manifestation of the central limit. If you've got supersonic turbulence, well, what that means is that if you pick a random point, it's being constantly run over by supersonic shocks and supersonic rarefactions. And every time you are hit by a supersonic shock, if you're isothermal, your density goes up by the Mach number of the shock squared. Every time you're hit by a supersonic rarefaction, it goes down by the Mach number squared. All right, now, so what you're doing is you're multiplying by a bunch of random numbers. Well, multiplying by a bunch of random numbers is the same as adding the logarithms of a bunch of random numbers. And you add a bunch of random numbers, no matter what the underlying distribution looks like, eventually you get to a guess. All right, so you multiply a bunch of random numbers, eventually you get to a log normal distribution. All right, so that's a sort of plausibility argument for why this should be the case. The width of this log normal turns out to depend on the Mach number of the turbulence, roughly is this. All right, here's again just a demonstration of this from a simulation. All right, the red points there are the measured density probability distribution in the simulation. All right, so can we combine these two things and make a plausible story for the origin of the iron? Well, it turns out that you can, and this is work done by these people. So the story is as follows. The kinetic energy per unit mass for an object of a characteristic size r, I can get just by integrating the power spectrum. I just integrate all the modes that will fit inside that region. Right, so I integrate from 2 pi over r to infinity, and I get r to the 3 minus beta, where beta is the negative power spectrum. All right, then I say, well, all right, that's the kinetic energy per unit mass. If I want to know if the region is gravitationally bound, I have to compare that to the potential energy per unit mass. All right, and the potential energy depends on the mean density, and the mean density required to be gravitationally bound is given by v squared over gr squared, which goes up by 1 minus b. The Mach number is a function of size scale, but that's just like the square root of the velocity squared versus size scale. It has this scaling. All right, so then I do the following thing. I say, at a given size scale, I think I know what the Mach number is, and so I know what the distribution of densities is. I know how dense I have to be gravitationally bound, so I just ask, what fraction of the density PDF, what fraction of the mass on this size scale is dense enough to be gravitationally bound? All right, and then I say, well, all right, bound regions on a certain size scale produce a characteristic density, or a characteristic mass, rho r cubed, and then I just integrate over all size scales and I get a mass distribution. And I have left out a god-awful amount of mathematics that I have just, simplified out. All right, in fact, this is closely related to the excursion set formalism used in cosmology, and in fact can be done in more or less exactly the same way. So that's pretty good. And when you do that, you get something that looks plausibly like the observed IMF. All right, there's a problem. Here's the problem. This gives you the mass distribution of gravitationally bound regions. It gives you the mass distribution of things that should be bound. So suppose I do this and I get some 50 solar mass gravitationally bound region. Let's call it a core, a 50 solar mass core. Will that give me a 50 solar mass star? Right, if I've proven that there's a 50 solar mass bound region, I haven't proven it's going to make a 50 solar mass star. And in fact, there's excellent reason to think it won't. So here's a simulation done by Claire Dobbs showing exactly that. She started with something like a 50 solar mass core, and then let it collapse, and lo and behold, it fragments into these little tenth of a solar mass objects. All right, and this result isn't that surprising, because you expect things to collapse into fragments of order of Jeans mass and size. And the Jeans mass at sort of plausible interstellar densities and sound speeds is about a solar mass. So why don't these 100 Jeans mass objects give me 100 little things instead of one big thing? All right, because if that's what happens, well then who cares that I got some 50 solar mass bound cores? There's no relationship between that and the IMF. So is this right? Is this really what should happen? This 50 solar mass object should fragment into a million little pieces? Well, there's reason to think maybe not. Right, the reason is real life is not quite that simple. So we're going to need to do some simulations. And we're going to have to, in particular, take into account the effects of radiation. All right, so I am going to now take a little diversion and tell you about how we simulate this. So this is a calculation that's done with an isothermal coefficient of state. But real interstellar gas isn't isothermal. Real interstellar gas gets heated up by the stars within it. So what are the equations that describe this? Here are the equations we would really like to solve. All right, here's the equation of mass conservation, momentum for the gas, energy for the gas, energy for the radiation, momentum for the radiation, and the radiation and matter are coupled by this lovely object called the radiation force density, all right, which involves an integral over the radiation distribution function. Now, we would like to solve these equations. The problem is we can't because they're really hard. All right, why are they so hard? Well, the reason they're so hard is that imagine I wanted to describe the radiation field in this room. What do I need to tell you? Well, all right, at every point in the room, that's 3 dimensions right there, I need to tell you about the intensity of radiation traveling in every direction. All right, I need 2 coordinates to describe the direction. And I need to tell you what it is as a function of frequency or photon energy. All right, so we've got 3 positions, 2 directions, and then 1 energy. So we're at 6 dimensions. 6 dimensions is very, very, very bad. Very bad. All right, why is it so bad? Well, all right, suppose I wanted to do my simulation at a relatively modest resolution of 100 elements in each dimension. Well, all right, that's 10 to the 2, and I have 6 dimensions, so 10 to the 2 raised to the 6th power, that would be 10 to the 12. 10 to the 12 is a lot of numbers, and that's for an incredibly crappy resolution of 100 elements in each direction. All right, so we give up and we say, okay, I'm just going to go home and drink. All right, but then after you get over the hangover, you come up with some ideas. All right, so what you can do is you can approximate this. All right, so first of all, the systems we're interested in are non-relativistic. So you can make the equations and you can expand them in powers of beta and you can drop all the higher order terms. Incidentally, you can't drop all the higher order terms, you need to keep at least 1 order in V over C. Turns out that if you don't, you can't actually conserve energy. Turns out that radiation hydrodynamics is fundamentally a relativistic problem and you can't write down a consistent, purely non-relativistic theory of it. All right. Since we're interested in regions that are highly optically thick, the optical depth is much greater than unity, the spectrum is in most places going to be close to thermal, so we can integrate out the frequency dimension and just assume that locally it always looks like a black body. Now that's not strictly true, and there are some potential errors with that, but we're going to do it anyway. All right, since it's optically thick, we can use what's called the flux-limited diffusion approximation, where we say that the radiation flux is just proportional to minus the gradient of the radiation energy density. Right, again, that's true under highly optically thick conditions. And if you make all those approximations and do, again, a shitload of math that I'm going to spare you, you get to these equations, and we've implemented these in the Orion. All right, so now we can simulate something like a star-forming region with radiation. But before we do that, let's do just a simple back-of-the-envelope calculation. Always, before you run the code, you always do the pencil and paper calculation, because otherwise you don't know if the code's giving you the right answer, and you're just putting your faith in, the God in the machine. All right, so why should we worry about radiation at all? Why is it important? Well, here's the basic reason. Young stars can be really, really bright. They can be really, really bright because they're accreting. I can get 100 solar luminosities out of a 0.1 solar mass star. How can I do that? Well, the answer is I just drop matter on its surface. If I put matter onto the surface of a 0.1 solar mass star at 10 to the minus 4 solar masses per year, that's not bright a little bit. All right, and that luminosity will then heat up the gas around it. All right, and that heating in turn will raise the gene's mass, inhibiting fragmentation. All right, now remember the gene's mass goes like temperature to 3 halves power. So here's a cartoon calculation of the temperature as a function of position around a forming star. So x-axis is distance from the star, y-axis is temperature, and the red line is the temperature distribution right before the star forms, before a compact object forms. Then a star forms, mass of 0.05 solar masses, and I'm just accreting onto it. So I can calculate the temperature as a function of position around it. This problem I can actually do analytically. Here's the temperature versus position. The second blue line is once it's up to 0.8 solar masses. All right, now let's think through the implications of this. I would at order 1000 AU, I've heated the gas up from order 10 Kelvin to order 100 Kelvin. All right, so I've raised the temperature by a factor of 10. The gene's mass depends on temperature to the 3 halves power. So I've raised the gene's mass by a factor of 30. That had better have some effect on how this gas fragments. All right, so it doesn't. All right, well, you just had to sit through equations, so now I reward you with movies. All right, so here's a little numerical experiment. We're going to take something like one of these bound cores that we're interested in studying the fragmentation of, and we're going to ask, does it make one big star or lots of little stars? Because that's the key question for whether turbulence can plausibly explain the tail of the IMF. So I'm going to do, this is an NHD simulation run with Orion. On the left side, I'm going to show you the results using an isothermal equation of state. On the right side, I'm going to show you an identical calculation using radiation. All right, you'll see that in both of them, things start to collapse. The black dot is the star forming. All right, and look at the isothermal calculation. Oh, fragmentation. All right, we got all these tons of little stars, exactly what we don't want. There's the radiant group. 2 stars. Yeah, 2 stars. All right, we got a binary, which is actually a good thing because the typical massive star is a member of a binary system. It's not a single star. All right, so when we put in the radiation, we get exactly what we were hoping for. A lot of the mass does go into one big star instead of the thing fragmenting into tons and tons of little stars. And so we actually get what we need for the story to work, that there's a direct connection between the mass of the dense structures and the masses of the stars that they form. But it only works because of the effects of radiation feedback suppressing the fragmentation.
Why is the star in the middle of the simulation to start with?
Just because the initial conditions of the simulation start with something that's centrally concentrated.
It's a point bomb solar mass star in 100 solar mass.
Initially, there's no star there, but it immediately collapses at its center and makes a star whose mass starts at 0 and grows. Does that answer your question?
More.
Yes.
Can you actually get an IMF for the thermal case?
The isothermal case, we do not get something that looks like the IMF, but we get a mass distribution that...
You have a distribution.
Yeah, we have a mass distribution. It doesn't look like the observed IMF, but we do get a mass distribution and we can't plot it. I think we did it in the paper. I don't remember exactly what it looks like, but we plotted it in the paper. Other questions? All right, so I've told you something about the peak of the IMF, or the tail of the IMF. Let's go back to that. Right, this is the real egg and genes question. This is the why is the characteristic star at a mass such that nuclear reactions can occur? Where does that come from? Right, if everything were powered up, thered be no need to explain anything special. All right, there's not a power law. There's a special mass, and it is really a special mass. Where does that come from? All right, now, if you took a class in star formation or you talked to someone who sort of thought about this a little, you would probably get an answer that involved, well, gas clouds fragmented the gene's instability. How do I get the characteristic mass of stars out of this? Well, I say the gene's mass is over square root of sound speed cubed over g cubed rho. All right, so I say molecular clouds have a characteristic temperature of about 10 Kelvin, and that's fairly constant, and I'll plug that in, get the sound speed, and I'll plug in a sort of observed density of order 10 to the 5 per cubic centimeter, and lo and behold, I get 0.4 solar masses, and I'm done with the model. All right, there's a problem with this argument. The problem is it's total bullshit. All right, why is it total bullshit? Well, the reason is, I pulled a fast one. Saying the temperature is 10 Kelvin, that's not so bad. Molecular clouds are pretty close to isothermal. How did I get that density? Well, the answer is I knew what I wanted to get out, so I put in the number that we give it to. All right, molecular clouds do not have a constant density. They've got an immense range of densities. I can find regions inside star-forming molecular clouds with densities of 10 to the 2. I can find regions with densities of 10 to the 8th. I picked 10 to the 5 because it made the numbers work out. But if I didn't actually know this in advance, if I weren't a bullshit you, I could equally well have picked 10 to the 2. And then I run the characteristic stars 13 solar masses. And that looks a lot less impressive. All right, but there's actually something deep going on here. This is not merely an exercise in guess. The fact that I don't know what density to put in, and that molecular clouds have a wide range of densities, is telling me something deep about the physics of isothermal turbulence. Isothermal gas is scale-free. It does not have a characteristic mass. All right, how can I prove that to you? Well, here are the equations of motion for isothermal gas. All right, I've got conservation of mass, conservation of momentum, there's the Lorentz force term, there's the gravity term, here's the advection equation for the magnetic field, here's the Poisson equation for self-gravity. All right, so naturally being a fluid dynamicist, the first thing I can do is look at these and say, let's non-dimensionalize that. So here are the non-dimensional versions of the equations, and there are 3 dimensionless numbers that describe this system. The Mach number tells me about velocity divided by sound speed. The alpha Mach number tells me about characteristic velocity divided by alpha speed. And the virial graph, all right, which tells me about the ratio of kinetic and gravitational potential energy. The fact that there are these 3-dimensionless numbers shouldn't surprise you. All right, I've described the system as isothermal, magnetized, and self-gravitating. All right, so what energies are there available in the problem? Well, there's the bulk kinetic energy, that's 1. There's the thermal energy, that's 2. There's the magnetic energy, that's 3. And there's the gravitational potential energy, that's 4. All right, there are 4 energies in the problem, so I can make 3-dimensionless ratios, and those fully characterize the system. This is just one way of doing it. I can make other equivalent ratios, but they're just 3-dimensionless numbers. All right, so here's the problem. In about one line of algebra, I can show that these 3-dimensionless numbers are invariant under this transformation. But the mass isn't. All right, so what that means in practice for those who are used to dimensionless numbers. Someone says, I did an isothermal simulation. I did a simulation of a fragmenting isothermal gas cloud, and it collapsed, and I got a bunch of stars, and look, it reproduces the IMF, it's got the peak in exactly the right place. Give me a Nobel Prize. All right, and you say, no, you're lying. And the reason you're lying is, you did your simulation in code units. You did your simulation in dimensionless units, because your simulation doesn't have a nice scale. And then you chose how to scale it to get the right answer. All right, but I can take your simulation and I can say, well, I don't think you're scaling. I think the characteristic mass of the star should be the mass of the Earth. And that's an equally good solution to the equations. Every bit as valid as the one where the characteristic mass is the mass of the sun. All right, so you cannot explain the existence of a characteristic mass scale using just the physics of isothermal gas. There's just not enough physics in there. You have to drop the assumption of isothermality to explain why the IMF has a characteristic mass scale. All right, I learned this from the advanced technique of dimensional analysis and nothing more than that. All right, so how do I give up the isothermal assumption? All right, well, one option is I could appeal to the fact that the molecular gas in the galaxy is embedded in the galaxy. It's embedded in this very large structure that is not isothermal. All right, so I've got some galaxy scale non-isothermal medium. All right, and then I say, well, molecular clouds have an outer scale where the isothermality breaks and everything is set there. All right, and I either can use the mean volume density at that outer scale and calculate the G's mass that way, or I can compute something like the median density or the mass average density, or for those who are in the know, that's equivalent to calculating it from the normalization of the line with size relation. Turns out these two are equivalent. All right, so is that a plausible explanation? Is that a plausible story? I would argue no, and there are a couple of problems. All right, problem one, so you need to pick the outer scale of the region you're interested in. You need to say what a cloud is, the outer scale of a cloud. Please identify for me the cloud in that image. All right, this is what star-forming regions actually look like. Please identify where you'd like to draw the density contour that defines the cloud. You see the problem. All right, now you can make a plausible choice that would get you the right IMF, but if you didn't know the answer in advance, I defy you to get it from this. All right, similarly, if you're trying to do it from the line with size relation, you have this problem with the normalization isn't actually constant. All right, here's the second problem. When you actually do simulations with isothermal turbulence, it's not at all clear that you get a characteristic mass scale out of the simulations at all. All right, so there's this paper by Martello that doesn't get cited much, and I think it doesn't get cited much in part because the results are sort of embarrassing. All right, what's embarrassing is they did a simulation of isothermal collapse and fragmentation, and they just kept upping the resolution. What they found is that every time they increased the resolution, they got these filaments that just broke up into more and more pieces. Characteristic spacing between these sink particles was always just one SPH smoothing element. All right? As a result, the characteristic mass they got, all right, so here's the simulation to the lowest resolution, you get this characteristic mass. Here's the simulation with the next highest resolution, you get this characteristic mass. Next highest resolution, this characteristic mass. The characteristic mass you get is always just the smallest mass you can resolve. All right, so that immediately tells you something's wrong. There's not enough physics here for this problem to even have a well-defined answer. So, if we give up on that approach, what can we do instead? What we can do instead is say, well, all right, maybe the gas isn't really isothermal. All right, maybe there's some subtle coupling between dust and gas that makes things not isothermal. And here there's some very, very nice work on this by Turbulence, who I think was a grad student here initially. So she did some simulations where she said, let me make the equation of state not isothermal. Let me give it a kink. And let's move that kink around in density and just see what happens. And what she found is that the characteristic mass you got out was basically just determined by the Jeans mass evaluated at the point where the equation of state had this kink in it. So when you change the equation of state, you change the characteristic mass. Good, that's encouraging. We're on the right track. We have a way of setting the characteristic mass by changing the equation of state and making it not isothermal. Now in real life, what makes the gas not isothermal? All right, so it turns out treating this as an equation of state is a pretty bad approximation. Here is a calculation done by Glover and Clark. Here's the x-axis density, y-axis is temperature, showing the temperature distribution in a simulation of theirs. And what you can see is that, there is no single density-temperature relationship. You can't describe this as an equation of state. Here's some work by Stella Hoffner showing the same thing. You can't describe this as an equation of state. So, what you can do, though, is again go back to doing simulations, including radiation. Now, before we do the simulations, I always do the simple analytic calculation first. So here's my cartoon analytic calculation of how we can use radiation to set the peak of the IMF. All right, so here's my molecular cloud, my theorist spherical cloud. All right, and I can describe it in many ways. I'm going to describe it in terms of its mean pressure, just because that's I already know if you don't like it, you could make a different one. And let's say a star forms in the center. All right, so here's my star, and my star starts accreting, it starts heating up the cloud around it. All right, so let's calculate the temperature distribution. The temperature depends on the position, which I'm going to characterize through the density, again, just because that's a convenient variable, and it depends on the luminosity of the star. So I know the luminosity of the star, that gives me temperature as a function. And that luminosity depends on the accretion rate, which depends on the mean density, that's this. And it depends on the escape speed from the surface of the star. That's this thing, modulo factor of √2. All right, because that tells me for every gram of matter I drop onto the surface of the star, how much light has to come out. All right, so I calculated the temperature distribution. I'm now going to make the following nonsense. Imagine drawing a little circle around the star, very small, and asking, how much mass is in that circle? All right, well, I draw a little small circle, there's not much mass inside. And then I can ask, material inside that circle, or the boundary of mass, which is the same thing with a factor of order. Well, the gas right near that star is very hot. All right, it's got a high temperature, and so it's got a very high Jeans mass. So within that little circle, there is much less than 1 Jeans mass worth of material. Right? There's not much material inside the little circle, and the Jeans mass is very high. And you can imagine drawing successively larger circles. As I go out, the temperature is dropping, and so the Jeans mass is going down. The mass enclosed is going up. So let me take very simple onsets. I eventually reach a circle where the mass enclosed equals 1 Jeans mass, and I say the stuff inside that radius can't do anything but go on to that one star. It can't go fragment to make another star. That stuff will all go into this star at the center. Everything else is free to go off and make other stars. So the characteristic mass of a star is simply the mass enclosed within the radius where the enclosed mass equals the Jeans mass. All right, the Jeans mass depends on the temperature distribution. All right, and this is, it turns out, a system of 4 equations and 4 unknowns, and you can solve it. And you can get a characteristic mass of a star in terms of this thing, which is the escape speed from the stellar surface. Here is where the magic happens. What sets the escape speed from the surface of a protostar? It's a subtle question. The answer is deuterium. All right, the escape speed from the surface of a protostar is determined by deuterium. Now, let me unpack that statement for you. All right, let me remind you, first of all, of your stellar structure class that you've repressed long ago. All right, remember polytropes. All right, for a polytrope, the surface escape speed is just determined by the central temperature. All right, if you know the central temperature for a polytrope, you can immediately calculate the escape speed from the surface. One determines the other. And it turns out that young stars are not exactly polytropes, but they're pretty close. It turns out that they're pretty close to fully convective. They're pretty close to n equals 3 halves polytropes. So you know the surface escape speed from the central temperature. What sets the central temperature of a young accreting star? Well, the answer is the same thing that sets the temperature in the center of the sun. The temperature in the center of the sun is thermostated by hydrogen burning. The temperature in the center of a protostar is thermostated by what it's burning, which is deuterium. Deuterium has an ignition temperature of about 1 million Kelvin, as opposed to 10 to the 2nd Kelvin. And that is what sets the central temperature of the star, and thus the escape speed from the stellar surface. All right, and you can actually calculate that temperature about 10 to the 6th Kelvin from fundamental constants. All right, so that's what sets the escape speed from the surface of the protostar. And you can then just plug that into the expression for the characteristic mass of the star. When you do that, you get to write down the characteristic mass of the star in terms of fundamental constants. All right, so the characteristic mass of the star is determined by the constants that go into this 10 to the 6th Kelvin. Those are the mass of a hydrogen atom. This theta C is a dimensionless number. It's basically, for those interested, it's the energy in the core of the star in units of the Gamow energy for the D to H reaction. All right, the fine structure constant, the gravitational fine structure constant, and it's almost entirely in terms of fundamental constants. There is a residual dependence on interstellar conditions. Depends on the pressure within the cloud, over the point pressure, to the minus 1/18th power. And believe me, I tried really hard to make that minus 1/18th go away when I did this calculation. And I couldn't. All right. Nonetheless, if you plug in characteristic interstellar pressure, all right, typically 10 to the 6 P and P over K units, you get about the right stellar mass. Now, you could naturally say, well, aren't you just pulling the same bullshit as in the Jeans mass argument? How did you know to plug in that pressure? How did you know not to plug in a different pressure? Didn't you just cheat to get the right answer? I plead guilty to bullshit to the minus 1/18th power. You don't like the pressure I chose? Go ahead and try your own. All right. Try 10 to the 12th. All right, 6 orders of magnitude. Well, all right. That's 10 to the 6th minus 1/18th. That's 10 to the 1/3 power, so it's about a factor of 2. So if you raise the pressure by a factor of 10 to the 6th, the characteristic mass of stars will go down by about a factor of 2. Wait. The cores of giant ellipticals. They probably have higher pressures the stars in them probably formed at higher pressure. Maybe 6 orders of magnitude higher based on their surface densities. This is a characteristic, this is a reason why the characteristic mass might be a little lower. All right? It's at least a plausible story. And let me, again, just remark, the other piece of magic we pulled off here is we now have a reason why the characteristic mass of stars knows something about nuclear physics. It knows something about nuclear physics because the nuclear physics is key to determining the radiation feedback, the strength of the radiation feedback, and that in turn determines the characteristic masses of stars. Suppose you made all the deuterium in the universe vanish. The first thing that would burn is hydrogen. Well, you'd get a higher characteristic temperature in the core before the stars stop contracting. The surface escape speed would go up. And when you work through the logic of the math here, if you make this thing go up, the characteristic mass of stars goes up to compensate. All right, so it's a nice story. Let me end with, all stories are nicer if they're accompanied by good graphics. So here's a movie where we're including this physics. All right, so here's a turbulent medium. We've got a bunch of stars that are going to form in it. Here I'm showing you the density structure. On the right I'm showing you the temperature. Under the stars, it's black. Start the movie running. Each of these stars has a protostellar evolution code running inside it that accounts for deuterium burning and gets the correct radius. All right, so I form a cluster of stars. Here's the mass distribution I get. So x-axis is mass and solar masses. Y-axis is fraction of the total stellar mass in that mass bin. The green line is the simulations. The gray band is what you would get by drawing an equal mass of stars from the observed IMF. All right, so the green line should stay within the gray band as the simulation runs. Lo and behold, it does. All right, the KS test says that the simulation mass distribution is consistent with the observed IMF, KS statistic of 0.3. All right, as a bonus, we also get right the binary fraction as a function of primary star mass. All right, so I will end there for those just waking up. The IMF appears to be a first-order universal linearity set. All right, it's got a characteristic peak mass between 0.1 and 1 solar masses and the power law tail of power masses. And the power law tail is plausibly produced by the statistics of supersonic turbulence, provided that we then throw in this bit about radiation feedback, stopping the more massive things from subfragmenting as they collapse. The characteristic peak mass likely comes from the effects of stellar radiation heating as well, and when you make a model based on that, you get to explain how it is that the ISM knows anything about nuclear physics and why it is that stars are nuclear furnaces. I will end there.
Thank you very much for this very interesting talk. So let's open for questions. We'll make a little bit more light now. And let's first open questions to the students and postdocs. Oh, yes, go ahead.
You said that the initial loss function is pretty much independent regardless where we look. It is at least in our way.
Yes.
So I, from my simplistic understanding of it, would expect that to be an influence of metallicity on the cooling timescale of clouds, but we don't seem to observe that. So are there any ideas why that would be the case?
Okay, so first of all, I should say that the range of metallicity is accessible to us where we can actually measure the individual stars is pretty small. All right, we can do this in the Milky Way. We can do it in the Magellanic Clouds. All right, so you can maybe get down to 0.2 solar in the SMC, but you can't go down to anything lower than that. All right, so that's the first thing is, understand we have a limited range of radiation. All right, now, why doesn't metallicity matter? So actually, Andrew Myers, who is a student who's working with me and some other people, looked at that in some simulations. All right, the answer is that the metallicity doesn't matter because the thermal equilibration time, the cooling time, so that you said, is 0. All right, it's tiny compared to any mechanical time scale. You reach thermal equilibrium at anything like solar mass, you reach it in 0 time. All right, take away 90% of the metals, so it takes 10 times longer to reach thermal equilibrium, that's still 0 time. Take away 99% of the metals, it's still 0 time. Maybe if you take away 99.9% of the metals, you drive metals down below 1% of solar, then you have to start worrying about things. But over a range of metallicities from sort of 1% of solar to super solar, you know, the time scale is still 0, so who cares how close to 0 it is?
I was wondering, first of all, I have two questions about the mass to light ratio in ellipticals, because it was my understanding that the stars that you see now in ellipticals were not formed when the galaxy was elliptical. So maybe some fraction of them were formed in the merger that actually caused the galaxy to become an elliptical. But most of the stars were born when they were disky galaxies. And then, so how come they knew that they were going to end up in an elliptical galaxy?
So I don't think they knew they were going to end up in elliptical. They probably did form in disky galaxies, but they formed in the most intensely star-forming, dense disky galaxies, right, at high redshift. They formed in the things that were the mass of the Milky Way already by redshift 3. Those things were really, really dense compared to star-forming systems today. So they didn't, you're right, form, in situ in the elliptical for the most part. But they did form in almost certainly significantly denser star-forming environments than what we have in the world.
But at least that your statement about the pressure inside the current day ellipticals should be moderated.
Fair enough. I think we don't really know what the pressure was in the redshift 3 systems where the stars and ellipticals formed. We just know it was big compared to a lot of galaxies.
And the other question I had was, does it's my understanding that your accretion luminosity for the different size objects that you're forming should be very different. So it should make a prediction for if we measure accretion luminosities for different size objects are going to be stars of different masses. We would expect to see quite different accretion luminosities.
Well, so the accretion luminosity depends on the escape speed from the surface of the thing and on the overall accretion rate. Right, so the escape speed from the surface actually doesn't vary that much. It's pretty close to independent from this. All right, and that's again because of this deuterium burning in the core. All right, so the thing that does vary is the accretion rate. All right, and it's certainly the case that different objects have different accretion rates, but I'm not quite sure where you think there's a prediction there that can be tested against this model. Okay.
Yes.
You just mentioned again that you started with it in your final derivation of your characteristic mass, that eventually the escape velocity is only linked to the central temperature for protostars at least. Can you comment on that again? Why is that true? Why does it hold for protostars?
Well, okay, so it is a generally true statement for polytropes. All right, so for a polytrope in general, the surface escape speed is determined by the central temperature. All right, so if you know and also the chemical composition, but that's the same for all of these stars. All right, so if you know this, if you know the central temperature, you know the surface escape speed. Now that's actually pretty close to approximately true even for main sequence stars today. They're not exactly polytropes, but it's a reasonably good approximation that the surface escape speed just scales with the central temperature. So more massive stars, O stars, do have higher central temperatures than the sun, so they've got higher surface escape speeds. All right, but it is a generally true statement that surface escape speed scales with central temperature. It's a result of the virial theorem, is one way to think about it. It follows from the virial theorem. I mean, the gravitational binding energy has to be proportional to the thermal energy, right? That comes from the virial theorem.
Okay, now let's open for everybody. Also, yeah.
For simplicity, you would assume that the stars have black body spectra. It is well known that real stars can deviate strongly from the black bodies, particularly in the UV regime, which is responsible for the ionization. Do you think that this is a problem?
Well, okay, so I did worse than that. I assumed the stars had no spectrum at all. I assumed they just dump thermal energy.
Okay.
So is that okay? Well, it depends on for what purpose. All right, now, these are environments that are extremely dusty. typical star forming region, if you go look at like the Orion Nebula cluster, and look at the stuff that's still forming stars when there's still gas. Typical visual extinction is 100 magnitudes. All right, so the mean free path of a photon coming off the surface of a star is about that big. All right, the photon goes a tiny distance, hits a dust grain, and is immediately absorbed. All right, and then it is re-radiated in the infrared. So I did not follow that first absorption, I just assumed instantaneous absorption and re-radiation. Is that problematic? Well, it depends on what you want to do. Now, I'm not in these simulations following the ionizing radiation feedback. If I wanted to do that, obviously, the approach I described would not work. All right. On the other hand, for figuring out the thermal structure of the gas and the temperature of the gas, it's actually a pretty good approximation to just ignore the spectrum of the star, because by the time I get anywhere more than a few tens of AU away from the star, all that radiation has been reprocessed. So it would make a difference in the central order 10 AU, but that's it.
So can I link this to the previous question on methodicity? If I change the methodicity by a factor of 10, I've increased my mean free path by a factor of 10. Does this change results in any case?
Right, so this is exactly the experiment we did, where we did a bunch of simulation with varying metallicity. And the answer is down to about 1% of solar no. And basically, it's again, because the mean free path is 0, so 100 times 0 is still pretty close to 0. So this will start to break down if you get a sufficiently low metallicity, where the condition for sufficiently low is when the mean free path for a stellar photon starts to become comparable to the size of one of these star-forming cores or clouds, so order of 10th of a parsec to a parsec. Once the mean free path is longer than that, the story will break down. But you need to go to a really low metallicity to make that happen, because you're starting from such a high optimal depth to begin with.
Further question?
So you sort of glossed over the binary fraction result. So is this just set by, in your picture, the radiation pressure?
Well, the radiation certainly has an influence in regulating how the stars form and fragment. A lot of it is simply n-body dynamics, though. A lot of it is simply that the massive stars, even if they don't form with a companion, will acquire one because they're born in dense regions and there are lots of other stars around them, and you tend to put the massive things together by n-body interactions. So I think it's a combination of the radiation and the fragmentation and just the n-body dynamics. And I have not explored sort of in much more detail exactly what combination of those two is.
What implications do the variations have for the brown dwarf mass regime?
I am reluctant to speculate that far because I'm not sure I trust the resolution of my simulations that far. What I can say is that brown dwarfs, all right, so brown dwarfs require that something had effectively gone wrong, right? So if I take this picture, all right, every star should be able to heat up a little island of gas around itself, and that island of gas should be of order a few tenths of a solar mass. So how do I get something smaller than that? Well, one answer is I could have this, available mass supply that's bound to the star, which does not be that big to begin with. All right, so I could set that turbulence. I could also have this thing be accreting, but then have something happen to it, have a shock run over it, have it encounter another star, cut off the accretion element. I do not know what combination of these gives rise to the shape of the IMF at the low mass end, and it's not something that naturally falls out of this formalism, at least as it stands now. So I'm not sure I have that much to say beyond that.
So your heat mass depends on the deuterium body. What about the total energy balance? How long does it take to burn out the deuterium which is there? And is there a limit for the time scale of forming stars?
Sure. So it depends on the mass of the star you're talking about. For a one solar mass star, for a sort of a star near the peak mass, it will burn deuterium for many millions of years. The time to burn through all the deuterium is significantly longer than star formation timescale. Typical star forming times are under a million years, maybe a million years if the age spreads in star forming regions. The deuterium burning timescale is significantly longer than
If not, then let's thank Mark.